So dear students, the video for today is application of Gauss's law. So we already discussed Gauss's law as the total electric flux through any closed surface is equals to charge enclosed by the surface divided by the permittivity of the free space. So using this particular law, we are going to do some of its applications. So first application is to find the electric field. To find the electric field due to M infinitely long straight uniformly charged wire. So quite long application, the topic, subtopic. So here there are two or three things that need to be noted down. So first one is infinitely long straight. That means our wire is infinitely long in length. It is infinite in length and it is straight, and again it is uniformly charged wire. Uniformly charged wire means all the charges are uniformly distributed on the wire itself. So let us draw the diagram. If this one is my wire, straight wire, and let us take the charge is uniformly distributed throughout its surface and it is infinite in length. So it is infinite in length. Now what we will do here is let us consider a cylindrical Gaussian surface around this wire. Cylindrical Gaussian surface around this wire whose length is L and whose radius is R. So I have considered our infinitely long straight uniformly charged wire, and around this wire I have considered a Gaussian surface, a cylindrical Gaussian surface of length L and radius R. Now if you see closely at the surface of this particular Gaussian surface, now what will happen is at this point on the surface of the at this point on the circumference or the surface of this cylindrical Gaussian surface, there are electric field contributed by each point charges. So this particular charge on the wire contribute the electric field in this direction. This will contribute the electric field in this direction. Similarly, this will contribute the electric field in this direction. So from this point, the length towards the downward is infinite, and even from this point, the length towards the upward wire is infinite, because the downward length is infinite and even the upward length is infinite. That means the total number of charges contributing the electric field at this point will be equals to the total number of charges contributing the electric field at this point. That means the contribution of this electric field will be towards this direction, and the contribution of this charges to the electric field at this point will be towards this direction. That means the net electric field at this point will be towards this direction. So at this point the net electric field will be towards this direction, that will be perpendicular to the surface itself, because from this point there will be infinite charges towards this direction, and again towards this direction the charges are infinite. Now you can take even another point, this point. Even at this point, due to these charges, the electric field will be in this direction, and there are infinite charges towards this direction, and again infinite charges towards this direction. So due to these charges the field will be at downward at this point, and due to the charges along the downward, the field will at this point will be towards this direction. So the net electric field will be towards this direction only. That means at every point on the surface of this cylindrical Gaussian surface, the electric field will be normally outward at every point, this way. And at this surface or at the perpendicular to this surface, there will be no electric field. Why there will be no electric field? Towards this direction, towards perpendicular to this surface, even towards the perpendicular to this surface, the electric field will be 0. Why it is 0? Because if there will be an electric field towards this direction, then the positive charge will move towards this electric field along the wire, because the electric field direction is towards this direction, and it will exert a force to this positive charge towards this direction of the wire. That means the charges will flow along the wire in this direction. But that is absurd. That is not considerable in this particular section, because we are dealing with electrostatics, which means the charges must be at rest, or charges cannot flow. Therefore, if there is electric field towards this direction, then the charges will start to flow, which will contradict our the topic itself. That is we are dealing with the topic electrostatics, so the charges must not flow in this case. Hence, the electric field towards this direction, parallel to the wire, cannot be accepted, and again towards this direction also electric field cannot be accepted. If there would be an electric field towards this direction, then charge starts to flow, and that is not discussion of our topic, because we are dealing with electrostatics, which tells us that charges must be at rest or charges cannot flow. Hence, the direction of the electric field will be perpendicular to this curved surface area only. Electric field will be perpendicular to this curved surface area only. Now, okay, let us calculate what is the total electric flux flowing out of this particular cylindrical surface. Total electric flux flowing out of the Gaussian surface will be phi is equals to electric field into the curved surface area. E dot A will be my total flux flowing out of the Gaussian surface, and since the only curved surface area will take part in this case, only the curved surface area will take part in this case, only the curved surface area, this curved surface area will take part in the contribution of electric flux in this case, and even the direction of the normal to the surface, so this is the normal to the surface, and direction of the electric field at those points on the surface are same. Therefore, the direction of area vector and electric field are same. So, theta is 0 in this case. So, phi will be just EA cos of 0 degree, and this will give me phi is equals to EA. where E is the electric field at each point on the surface and A is the area of the curved surface of the cylindrical. Now let us utilize our Gauss's law, which tells us that the total electric flux flowing out of this Gaussian surface should be equals to charge enclosed by the surface divided by free space permittivity. So according to Gauss's law, according to Gauss law, the total flux out of this Gaussian surface will be equals to charge enclosed by the surface divided by permittivity of the free space. So if this is my Gaussian surface, what will be the charge enclosed by this Gaussian surface? We don't know, isn't it? Because what is the amount of charge lie on this charge wire? Still we don't know. But what we know here is this portion of the wire is the this portion of the wire contains the charge that is enclosed by this Gaussian surface, and we know the length of this wire from here to here, that is the length of the Gaussian surface itself. That means Gaussian surface will enclose L amount of length of the wire, and if lambda is the charge per unit length of the wire, and if lambda is the charge per unit length of the wire, then total charge enclosed by Gaussian surface will be equals to lambda into L, because lambda is the charge per unit length, and if you multiply that charge per unit length with the length of the Gaussian surface, then you will get the total charge enclosed by the Gaussian surface. That means this Q will be equals to lambda into L, where lambda is the charge enclosed by the lambda is the charge per unit length of the wire, and L is the length of the Gaussian surface, or it is the length of the wire enclosed by the Gaussian surface. Hence phi will be equals to lambda L divided by epsilon naught. So this is your phi from Gauss's law, and this is your phi from electric flux. So comparing, suppose this is equation 1, this is equation 2. So comparing 1 and 2, will get EA is equals to lambda L by epsilon 0. So EA is equals to lambda L by epsilon 0. Now what is E? E is nothing but E is the value of the electric field at each point on the Gaussian surface, that will be equals to, or okay, E is the value of the electric field that we are going to calculate, because our sole aim is to calculate the electric field due to this wire, infinitely long straight wire. So E we need to calculate here. So E into, what is A? A is the curved surface on area of this cylindrical Gaussian surface, only the curved surface area, because this area do not contribute to any flux, as I've told you, because there is no electric field towards this direction and this direction. So curved surface area of this Gaussian surface is nothing but it is 2 pi r L, will be equals to lambda L by epsilon 0. So L and L gets cancelled. So E will be equals to lambda divided by 2 pi r epsilon 0. So this is the value of electric field, and the direction of the electric field is normal to the surface. Electric field is towards the normal to the curved surface. So the direction of electric field can be given by the normal vector n cap. This is the normal vector which is perpendicular to the curved surface area of the cylindrical. So this is the value of the electric field at a distance of r from this infinitely long wire. So at this point, that is at r distance, electric field is lambda by 2 pi r epsilon 0. If I consider this point, which is at a r1 distance, then at that distance the value of the electric field will be lambda by 2 pi epsilon naught r1. That means all the things are constant, only thing that varies is r. So if you go very far from this infinitely long straight wire, the radius is going to increase. If radius is going to increase, then the value of the electric field will keep on decreasing. So if we have an infinitely long straight wire, the value of the electric field near this wire will be more because it is inversely proportional to the radius. And if you keep going away from this infinitely long wire, the value of the electric field keep on decreasing because E is inversely proportional to the R, which is the distance or the radius of the Gaussian surface. So this is it for today.